Energy sources come in renewable and non-renewable types. We've already covered the non-renewable energy sources. There would be nuclear power and the fossil fuels, coal, gas and oil. And now we're going to move on and do the renewable energy sources. We're not going to cover every single minute type of renewable energy source that's out there. We're going to hit just a select few. One thing we can see on this slide is the price of generating electricity. Now, one of the things that is true is these prices change constantly. As innovation and research takes place, the prices are fluctuating all the time. If you watch the price of gasoline, you'll see how the price of gasoline fluctuates all the time, and that's an energy source that we know how to make, we know how to produce, and really not a lot has changed, and yet we still see wild fluctuations in price. So for example, at the moment our slide here is saying that solar photovoltaics are producing electricity about 30 cents a kilowatt hour. And the price of that has actually dropped a little bit since the slide was made. It's in the mid 20 cents range. Nuclear power, we can see that it's 10 to 21 cents. Notice the bars colored in a little bit different there. So nuclear power is actually selling electricity round about 3 or 4 cents. But this 10 to 21 cents would be if we actually were including the price of containing the nuclear waste. So that's more of a realistic cost than the actual cost of nuclear electricity. And we'll go through the other solar systems, but on the whole, you can get average for solar is about 20 cents a kilowatt hour. So wind power has actually gone down at the moment. Wind power is roundabout in that 4 to 7 cents a kilowatt zone. So where do we need to have it to be competitive in the marketplace and actually make a profit? Well, electricity sells for about 8 cents a kilowatt hour. So if you were to look at your bill, you'll see that you're being charged about 8 cents for every kilowatt that you're using in your home. Now, to make money, the electrical generating company needs to be able to make its electricity for about 4 cents a kilowatt hour. So coal power is making electricity at the moment for about 4 cents. Natural gas is slightly cheaper than that. It's making it at about 3 to 4 cents. Hydroelectric about 4 cents. Wind power is in that 4 to 5 cents, so it's a little bit more expensive than it should be. Solar power is really making it in that 6, 7, 8 to 20 cents, so that's more expensive than it needs to be. Nuclear power, if you include getting rid of the waste, is way more expensive than it needs to be. So, obviously some of our fuel sources are economical to use, and some of them are not economical to use. So what we need to do is go through our renewables, see which ones are economic to do now, and which ones may become economic in the future if we do enough research and development and get our technology better. One thing that's definitely true is that the cost of generating electricity using renewable resources has dropped dramatically over the last 20-30 years. The price of making electricity using solar power has dropped dramatically since about 1988, and now it's getting close to a point where with a few more tweaks you could actually do it sustainably and still make a profit. Wind power has dropped dramatically, and with new technologies you can now build wind that will make it at about 4 or 5 cents a kilowatt, making it close to what coal and oil are actually making electricity for. The price of coal is only set to go up because it's a non-renewable resource, and as we start to run out, the price will increase. Price of nuclear power is definitely going to go up if we include trying to get rid of the waste. So renewable energy prices are dropping. As research and development continues, the price per kilowatt goes down. Non-renewable prices keep rising. the price of having to clean up coal when we include cleaning up air pollution, the price of having to seal away the waste when we're talking about nuclear power keeps adding to those costs, as well as the fact that the fuel sources themselves are non-renewable and therefore becoming depleted. They become rarer, and because of supply and demand, their cost goes up. So if we're going to get a sustainable society, we have to look towards renewable energy sources. And those renewable energy sources need to be producing energy at about 4 cents a kilowatt. Around the world, renewable energy sources provide almost 13% of the energy that we use. Now you got to remember that most of this is going to be in less developed nations, and they're primarily using biomass as their energy source. Now biomass may not be able to provide enough energy to run a modern economy like that of the US, so we need to look through the different types of renewable energy sources to see which can actually support an industrial nation. The first thing to understand is that no single energy source will support an industrial nation if it's completely renewable. You have to diversify if you're going to use renewable energy sources. Solar power will not work in every area of the country. Wind power does not work consistently all the time in every place. You have to have a diversified energy structure. And the plan is not to get rid of non-renewables altogether. We can use non-renewable resources as long as we use them at a slow rate so that we don't run out in the very short term. So what we should be using is some natural gas. Natural gas is available in large amounts, provides extremely high quality energy source, and is very low pollutant. Biomass, which we can produce and is totally renewable, can also be converted into natural gas, so we get a large amount of biomass. Obviously you can't cut down trees and use their wood to feed the industries of the United States, but you can convert biomass into gas that's usable or electricity. The primary renewable energy source would be solar radiation. Virtually all of the other energy sources we're going to look at, or already have looked at, are just packaged solar radiation. So why not jump to the front of the queue and just use the solar energy directly? Don't convert it into evaporated water and then rain and then use that energy. Don't package it into plants and then convert those plants into oil and use that for energy. Just utilize the solar energy as it comes onto the planet. The sun produces way more energy than the nations of the world need every day, so if we can find a way to harness it, it's an extremely efficient and long-lasting source of energy. If you look at the map, you can see that not every state in the United States can use solar energy all of the year. Some parts of the United States just do not lend themselves to being good solar energy producers. What we need is areas with large amounts of sunlight during summer and winter, where that sunlight is going to happen every day. It's not going to be cloudy for weeks on end, so that we can collect our solar energy efficiently and produce stable energy production. So when you plot that on a map of the United States and Canada, this is what we see. Obviously Alaska would not be a place where you'd want to try and run your economy on solar energy. But down towards the southwest and southeast, there is solar energy available most days out of the year at a rate of delivery suitable for producing electricity. So as we were saying before, one of the things you cannot do if you move to a renewable energy system is say it's a one-size-fits-all energy producing world. Energy in Michigan from solar radiation will not be continuous enough or of high enough quality to be able to put solar thermal power plants and expect them to work. Whereas if you're working about New Mexico, then for most of the time there is harnessable solar energy there that can be used to make electricity, and therefore some states are going to have to be exporters of electricity made from solar energy, and some states would have to be importers of electricity from solar energy. Electricity is not the only way to use solar energy though. Solar energy can actually be produced three basic ways. The first one is just passive solar heating, and I'm sure we've all parked our car in the summer, gone to college or gone shopping, and then come back, open the door and jumped in the car, and it's just a furnace. Particularly if you've got vinyl seats. If you've ever known somebody with a car with vinyl seats and you jump on the seat and your skin just sears to those seats, you know exactly what I'm talking about. Well, that's an example of passive solar heating. You didn't do anything to make the car warm, you just parked it in the sun, and because of the physical nature of the materials the car is made from, the inside warms up. It gets hotter and hotter. The inside of the car becomes much hotter than the air around the car. The way that works is that the solar energy passes through the glass of the car, through the windshield, through the back screen, through the windows. And when it passes into the car, it changes. It's not now just light, but when it interferes with the other materials in the car, it actually becomes infrared. It becomes heat. And that heat can't pass back out through the glass, therefore is trapped inside the car. So passive solar heating just needs an area of collection, which is normally going to be glass, and an area of absorption, the place where the heat will be collected. There's no pumps, there's no special way to make this happen. All you have to do is just do a design where you have an area that lets the light in and an area to collect the heat. So the heat collection could be a concrete or stone floor area, or it could be a fluid area for actually warming up a fluid. This is an example from a house in Atlanta. This house belongs to the South Face organization, and they're an organization designed to helping people build renewable and high efficiency housing. So the windows let in sunlight, and our floor is a thermal tile and a very high thermal density concrete. So what happens is sunlight comes in, heats up the floor, and then throughout the rest of the day that floor radiates back that heat. Now in Georgia it's not heat that we really need. As I sit here doing this, it's 101 outside. So you can see that the room looks dark. That's because there are shades sticking out over the windows so that in the summer the heat does not make it onto the flooring. During the winter, this room is providing large amounts of heat for the house. My parents still live in England, and they have a system that's very like this. They have on the right hand side of the diagram here a conservatory, a glass walled room. Sunlight comes into that room and makes it hot, and there's thermal flooring at the base of the room there. That thermal flooring absorbs the heat and passes it into the rest of the house. So at my parents' house, the conservatory will absorb heat up the floor, and then pass that heat into the dining room adjacent to it. So the warmth will pass through the floor, and the floor will be warm to touch. That floor then radiates the heat into the rest of the house. So in the winter time, heat is collected outside the house in the conservatory in the glass filled area and passed into the rest of the house. In the summertime, you have to put shades up and you have to insulate the floor to stop heat being passed into the room. Now of course that's not a problem because we're in England, so summer's only 3 weeks long. A very different problem than we find here in Georgia, where cooling the homes is the most important thing. So that was a passive solar system. The heating just happens, and the heat is then passed to other areas of the rooms. With active systems, you have to actively move the heat from one place to another. You're actively collecting it at a series of collectors and then depositing the heat elsewhere. So an active system always is going to have a pump somewhere, and that pump will be pumping a fluid or blowing hot air through the system. So you're deliberately moving the solar energy, collecting it and moving it to where you're going to use it. Now, a classic example of this is in a building in Sacramento that I visited recently, Sacramento, the capital of California, where they have some college buildings that have active solar heaters on their roof. Now, when you go to college, students always, need to go to the restroom, and after they go to the restroom, they should wash their hands. So all colleges have water heaters that are heating the water so people can wash their hands. And those water heaters are either electric or gas. They use large amounts of energy, but studies show that very few students ever actually benefit from it. A large number never bother to wash their hands after using the restroom, and the rest of them turn the tap on, wash their hands, turn the tap off before the hot water has ever even made it to the sink. So this building in Sacramento, they designed it so they could put water pipes over the roof. So embedded into the flat roof of this building, right underneath the black tar sealant, are a series of water pipes. And all day long the sun beats down on the roof. Now, if you've ever left a garden hose out in the middle of summer and the garden hose is just sat there filled with water with the sun beating on it all day, and then you turn the water on, that first water that comes out of the hose is extremely hot. Well, that's the idea here. Water's sitting in pipes up on the roof. The heat from the sun warms that water up, and then the pump pumps that water down, and that water is what people are using to wash their hands. So during the summer months, they're using very little electricity or gas to heat the water up to a comfortable hand washing temperature. During the winter, they just turn off the section on the roof there, and it just goes back to an average normal water heater type system. So this is what that system in California would look like, with the solar collector absorbing energy up on the roof of the building and the water then being fed down towards where people are using it. And it doesn't have to be on the roof of the building. Also in Sacramento, there's a building where the parking lot is the solar collector. The water pipes run underneath the parking lot. Every day in summer, the parking lot absorbs a large amount of heat, heating up the water for use in the building. Now, this is an active system because of the pump. The fluid is being moved through the solar collector. It's being pumped and collected energy in one area, and then that energy is delivered to somewhere else. So in an active system, there must be a pump. So passive systems, no pump. It's just fed through, just through the natural flow or the movement of the heat. Just normal, natural movement from an area of high concentration to an area of low concentration along its concentration gradient. Active systems, there must be a pump. We've got to physically be pumping a collecting fluid to a solar collector and then bring it back into the area where it's going to be used. Both passive and active systems, though, are only useful in heating areas. If you live in Georgia, you do that during the winter months, but for most of the year we're more interested in cooling areas. And if you want to run your computer, or you want to run your lights, or you want to run your TV, active and passive solar systems won't do that. So a more interesting way is to turn solar energy into electricity. How can we harness that solar power and use it to make electricity? And there are two different ways of doing that. The first is called a solar thermal power plant. So solar thermal, so sun's heat. Now remember, this is a power plant, and in most power plants what we're trying to do is boil water. So in a solar thermal plant we're going to collect sun's energy and use that energy to boil water. In most plants that involves a helostat field. Helostats are focusing movable mirrors. They have to move because they have to track the sun as the sun moves over the sky during the day. They're focusable because they're going to focus that solar energy. If you've seen Toy Story, the boy grabs Woody and he uses his magnifying lens to focus the sun and burn Woody's head. So that's what we're trying to do here. We're trying to collect large amounts of sunlight and focus that energy so that we can collect it and use it to boil water, so we can run a turbine, drive a generator and make electricity. Now obviously this is going to use large amounts of space. Solar thermal power plants use a lot of land because you've got to have a lot of area for those mirrors. Here's one example of a solar thermal power plant. The heliostat field that's using up all that land is focusing its sunlight onto these bounce down mirrors. Now again, the bounce down mirror is focusable. It can change its focus to get the maximum concentration of the sunlight, so that the mirrors are bouncing the sunlight back onto these focusable mirrors here. This bounces it down to this collector. Right? This is the outside view, and at the same time you can see that there's mirrors in here that are also focusing the light. They're moving the light down, making it more and more concentrated. This is the top looking down that collector. So the solar collector is focusing the light all the way down to the bottom, where there's a plate of maybe 3-4 inch steel, and that's where all that sunlight is being focused. Now that sunlight is extremely concentrated at this time. So to stop the metal plate from melting, from burning, it has a coolant flush by it, and that coolant's just water. So there's continuous water flowing behind the metal plate at the bottom of this cone. That water absorbs all the heat, flashes to steam, drives the turbine, spins the generator, and that makes our electricity. This is a different type of solar thermal power plant. This one doesn't have a bounce down mirror. You can see the heliostat field, and the heliostat field is focusing all the sunlight into the black cylinder, and the black cylinder is therefore boiling the water, and then the steam comes down into the cream square building on the right hand side there, and that's where the generator is. So solar thermal energy is collecting sunlight and using it to produce steam so we can make electricity. It does have the downside that it takes large amounts of land. It does have the downside that not every state can use this, only certain states, because you need to have sunny weather. You're going to have sunny weather for most of the time. It'd be no good if you live somewhere where it snowed and all the mirrors were covered with 2 foot of snow. It's got to be in a sunny place. New Mexico is our example. But even with those downsides, there's another downside that happens all the time, and that is night. At night there is no sun. At night is when everybody comes home and turns on their lights and turns on their TV and wants to cook dinner, and we get a big spike of electricity use right when the sun goes down, right when our power plants would no longer be generating the electricity. So to the left of the center there is a big silver building. Looks a bit like a battery, and that is a natural gas container. So during the day this power plant runs on solar energy, and each night it runs on natural gas. So it's got a natural gas backup. Now, downside right there. It means that this power plant is more expensive to build. You've got to build a gas plant and a solar thermal plant at the same time. It's going to be more expensive. Upside, the natural gas lasts you twice as long because it's only being used at night. During the day, it's using solar energy. Any other upsides? Of course there are. National security. The USA has its own sunlight. We don't have to import it from anyone. Sunlight's right here within our borders. Nobody can stop the sun coming out. So it is very good for national security. Economic security. It's our own sunlight. We're the ones producing it. So it does have benefits in terms of natural security. Pollution. During electricity production, solar thermal power plants are producing no pollution whatsoever. They do decrease the workforce though. Solar thermal plants need very few workers. Most of it's controlled by computers. So compared to coal, where we have all of the coal miners, all of the railway engineers, all of the railway builders to deliver coal to our power plants, nobody has to work to deliver sunlight. So the number of jobs in the industry is significantly less, and at a time when our economy is struggling, when we have a high unemployment rate, getting rid of jobs can have some very negative impacts. So this is a slightly different solar thermal power plant. This is a non-central collecting type. So rather than all the heliostats collecting the solar energy and focusing it into one central point, this is more of a diffuse power plant. Each individual heliostat focuses the light onto the black bar running down the center there and boils the water inside that black bar. It saves the need for having to align all of the mirrors, and so this makes it just a little bit cheaper. It's not quite as efficient, but it makes it a little bit cheaper without having to align all of the mirrors with that central collection area. So solar thermal plants aren't working at night, but they are generating electricity close to the amount that we need to generate, close to that 4 or 5 cents a kilowatt hour. This next one is solar panels, and the correct term for solar panels is photovoltaics. Now, photovoltaics have been around for a long time. I'm sure you've got a calculator that runs on a solar cell. I'm sure that you've seen watches that run on it. You can buy battery chargers that are photovoltaic. So for producing small amounts of electricity, photovoltaics are excellent. The space station, the International Space Station, has tons of solar panels and produces large amounts of electricity for itself using photovoltaics. But the space station has got a big advantage over the rest of us. Number one, it's out in space, so there's no clouds to cover up over the photovoltaics. There's no rain or snow landing on it, and the energy from the sun is much higher out there, and also you can position it so it can stay within the sunlight much more often than your house can. You can't position your house to make sure the sun is always going to strike it. So photovoltaics have a lot of the same downsides as normal solar power. They also are slightly more expensive to produce. So photovoltaics do not produce energy in that 4 cents per kilowatt hour slot that we're looking at. They are more expensive than that, really pushing up in the 10 to 20 cents per kilowatt. Don't think that the solar photovoltaics have to look like a big nasty solar panel like you see out on the space station. This section of roof is actually shingled with photovoltaic shingles. Now the photovoltaic shingles here are deliberately a black color so you can see which ones are the photovoltaics, which ones are the normal shingles. They wouldn't have to be that color, they could just be a more blended color so that you wouldn't tell. But the photovoltaics just come as a sheet, looks just like shingles from normal. And what you do is you wire them together as the roof is put together, and as they snap together they generate electricity for the house every time the sun shines. The cost of those photovoltaic shingles really makes them out of the reach of most people though. So if we're trying to provide realistic energy sources, photovoltaics at the moment just do not provide cheap enough electricity to supplement what we're doing with natural gas. So when we're looking at solar power, solar thermal power stations supplemented with natural gas seem to be at the moment the most economic renewable source. After solar power, we're now going to move on to wind power. And with wind power, all we do is we miss out a step. We're no longer going to boil water to generate steam, have the steams turn a turbine, and that turbine spin the generator. The turbine becomes the windmill. So the turbine is spun by the wind. So there's no boiling water here. It's a new system. So we're just going to take a windmill, let the wind blow the windmill around. That is the turbine. That turbine will spin the generator will make the electricity. A wind turbine generating area is often called a wind farm. So here's a wind farm found in Scotland. You've got to find a windy area. You need to put up your windmills, and then those turbines have to generate the electricity. Now that means you can only put them in places with large amounts of harnessable wind. George W. Bush's administration did a survey to see if there was enough harnessable wind energy in the United States to actually make an impact on our energy supplies. And their study suggested that just the Dakotas alone had enough harnessable wind energy to supply the electrical needs of the entire United States. So harnessable wind energy is out there. Now, of course, there are some problems. One problem is the places that have lots and lots of harnessable wind energy tend not to be the places where all the industry and homes are. So they tend to be in more wilderness areas. So we have the problem of, should we be destroying wilderness areas to build wind farms? And then we also have the problem of, well, how do you deliver all of the energy that's produced there to our large industrial areas? So if you're going to use wind power, you have to have a very robust national grid system. There's a series of power lines that spread throughout the nation to deliver power where it's needed. The problem of using up wildlands for our wind farms can also be overcome. One of the main benefits of wind power is that you can still utilize the land for other resources. If you have a nuclear power plant or a coal plant, that land is not being used for anything else. It is a coal plant, it is a nuclear plant. But if you have a wind farm, you can still continue normal farming right underneath it. You can grow your corn, you can grow your cows, you can grow your sheep. You can continue to utilize that land for any other purpose that you need. You can have an apple orchard right underneath it. And you don't even have to have it on the land. And there are a number of wind farms that are offshore. And this is an offshore wind farm. And what I want to do is switch to the next slide, just so you can get an idea of just how large these wind turbines are. Now, surprisingly, the number one most often quoted reason for not putting up wind farms would be aesthetics. That is, people saying that they're ugly. And it's one of the weird things that I would guarantee that a coal plant is always ugly. A nuclear plant is always ugly. And given the choice of a coal plant, a nuclear plant, or a wind farm, wind farms would definitely be the least ugly of the three. I'm not saying they're not ugly, but given the choice of having to produce electricity or not making electricity, of the types of power plant that you could use, wind farms are probably the least ugly. They do have some real problems though. The book probably talks about them killing birds, and the amount of birds killed has dropped dramatically because the modern wind turbines spin much slower. Their main problem is the wind. The wind does not blow consistently at the same speed. It comes in fits and spurts, and therefore the electricity that's produced is not consistent in its amount. So unlike your car battery that always provides 12 volts, unlike the electricity that's coming to your house that's always 110 volts, the wind turbines spin faster and then slower and then faster and then slower. So they tend to peak and then drop off, peak and then drop off. So you don't get a nice constant steady supply of electricity. That is incredibly difficult to deal with. You cannot allow these spikes in the electricity system. Imagine what spikes of electricity do to your computer. When it gets one of those little things, it just turns off. So you have to be able to even out the flow of electricity. And on a non-windy day, that means you have to supply extra electricity from another source. So again, we're back into, you can't just use wind power on its own. On a non-windy day, you got to get your electricity from somewhere else. So that's pushing the price up, because you can't just have a wind farm, you got to have a natural gas plant that can produce electricity when you need it to. So there's two areas there that we definitely have to overcome. Number one, we've got to even out the amount of electricity that comes from the wind farms. It doesn't matter whether the wind's blowing at 10 miles an hour or 50 miles an hour. It doesn't matter whether it's smooth wind or really gusty wind where it's blowing hard one minute, blowing softly the next. The power plant has to produce a nice steady, even amount of electricity. And if we can do that, then we've just got to overcome the problem of even when days when it's not windy, where do we get our electricity from? On windy days it's easy, you get it from the wind. But on non-windy days, where do you get that electricity from? So if we can fix both of those, then wind energy becomes viable. Because there's plenty of wind around the United States, it would be good for national security. And as long as we're building the wind farms here, it would be good for the economy. The last renewable energy source we're going to do is biomass. Now, biomass is bio-life mass, stuff, is stuff produced from living things. So biomass, as we've already said, is the number one fuel for people in less developed countries. But how can we in more developed countries use biomass as an energy source? There are four main sources of biomass energy: fuel wood, municipal industrial wastes, agricultural crop wastes, and energy plantations. Fuel wood, as the name suggests, is cutting down trees and utilizing the wood for energy. Right? Burning wood produces large amounts of air pollution. If you've ever sat next to a campfire and had the smoke blow in your eyes when you're trying to actually cook your hot dog or cook your s'mores, you'll know about the pollution that's in that smoke. It gets in your eyes, you can't see, feels like you can't breathe. And wood itself is fairly slow growing. So there's no way we could use fuel wood to support a industrial society. It doesn't grow fast enough, it's too polluting. Crop residues and animal wastes are a different idea. This is now not growing trees and using those for energy. This is utilizing scrap, trash, waste. Now if you think about corn, when we grow corn, we grow a field of corn. What we take away from that corn is the actual corn kernels, and what we're left with is the cob and all the shuckings and all of the leaves and all of the stems. That's our crop residue, that's what's left. When we go wheat, we'll take away the seeds and we're left with everything else. If we have a pig farm, we want to eat the meat from the pig, but during its life that pig produces large amounts of dung, and that dung is our biomass residue. Now, because this is a leftover, this is now not being produced deliberately as an energy source, it's just leftover materials. It does have large amounts of usable energy. We haven't used any energy to produce this. We were growing these crops, farming these animals anyway. This is leftover stuff. So how can we get that energy out? We collect the energy from those crop residues in exactly the same way as we would collect the energy from an energy plantation. The difference being that energy plantations are deliberately grown to generate our biomass. Now the downside here is that we are growing a crop specifically for energy use, and that always has the downside. The downside is we're producing a crop using lots and lots of energy input. We're putting into the crop diesel fuel because we're using a tractor to plow the field, diesel fuel because we're using a tractor to plant the field, diesel fuel because we're using combine harvesters to collect the crop. We're using oil products because we're using pesticides and herbicides on that crop. We're using natural gas and oil because we're generating fertilizers for that crop. So when we look at all the energy that we put into our energy plantation, the actual net amount of gain that we get is usually quite small. So actually using an energy plantation is not as efficient as using crop residues. A classic example right here is corn. In the United States, we've been obsessed with you getting energy from corn, using corn to make ethanol. The problem being that you have to put large amounts of energy into that corn production before you can actually use it to make any ethanol. And normally we'd be eating the corn. So as soon as you use corn as an energy source, the price of corn to eat goes up. So we're removing a food source to gain an energy source. Doesn't seem to make a lot of sense for most environmental scientists. So I got a bit off track there. What we're supposed to be talking about is, so how do we use our crop residues to make energy? And there's a couple of different ways. We've got direct combustion, ethanol production, and anaerobic digestion. Right? So notice that it's now making stuff around about 8 cents a kilowatt. It's a little bit too expensive to work right now. We definitely have to utilize some more research to get this down to the 4 cents a kilowatt that we need. So let's go through each one and see how they work. Right, the first one is direct combustion, and as the name says, it's directly combusted. You just take your crop residue and you burn it. So you could grind it up and feed it into a coal-fired power plant as a supplementary food fuel item. You could feed it into a trash burner, an incinerator, just as a supplemental fuel for that incinerator. Not the most efficient way of doing it. The only thing you can use of the product of this is electricity. That's what you're generating. And of course, with our economy using so much electricity, it's very hard for us to generate enough residue to support a high energy use economy like that of the United States. Number two, that was ethanol production. And the state of Georgia is really pushing ethanol production here. In exactly the same way that you would make whiskey, you would take a crop, you take those seeds, you ferment the seeds. Those fermented seeds then get distilled, and the alcohol, the whiskey, is produced from that. What we would do is we would take this organic material, we would ferment the organic material, you would make alcohol from it. That alcohol is then distilled off, and you produce alcohol that can be mixed with gasoline or used instead of gasoline. To do that efficiently is extremely difficult. There are two basic ways of producing this alcohol. The first is fermenting the sugars. The second is fermenting the cellulose or lignin. Now, the fermentation of sugar is what we do at the moment because it's nice and easy. At the moment in the US we grow corn, we collect the corn syrup, the corn sugar, and then we digest that corn sugar down with bacteria and it produces alcohol. We ferment it and generate the alcohol. And that's no different than making whiskey. It's no different than making wine, no different than making beer. It's nice and simple. We convert sugar into alcohol. The problem is we're using a food product, a sugar, to generate our alcohol. What would be much more beneficial is if we could turn the cellulose, the non-food product. Cellulose is the leaves and the stems. You can't digest cellulose. Or the lignin is wood, the product that is wood. If we could digest those down and convert those to a sugar, use an enzyme that would break those down to make sugars, and then those sugars would be converted into alcohol. It means we could use waste products. So all the paper that you throw away could be converted into alcohol. All of the grass clippings could be converted into alcohol. Or we already talked about the corn stalks and corn shuckings and the corn on cobs. All that would be converted into alcohol. Any leftover pallets, any leftover building materials just ground down and could be converted into alcohol. Any wood material would be made into alcohol. That would be by far the most efficient, because then for every crop you get to produce the food crop, and everything else that's collected could be converted into alcohol. The hard step in there is the enzymes needed to digest down that wood or that cellulose so that it becomes a sugar that can be used by the digester, by the fermenter. Now, a lot more research needs to be gone into that area before we can do this efficiently. Here in Georgia, we recently had 2 plants built within the last 2 years just to produce alcohol from wood, and one of them lasted less than a year before it went bankrupt. The technology is just not quite there yet. Georgia wants to go this route because we use large amounts of wood for our chicken farms. Our farms do a type of chicken rearing called deep litter, where the chickens live on a bed of pine shavings, and when they're finished, that chicken mess, the chicken poop and all the pine shavings are a waste that has to be gotten rid of. Well, that's a prime feed source for a digester. If you could have a ligase digester, get the lignin in there, digest it down, make the sugar from it, it's a huge source of energy. And hopefully Georgia will actually get through that research and be able to make large amounts of energy from that. We are not there yet. And the last type, that would be our anaerobic fermentation. Instead of breaking it down and turning it into alcohol, this time we'd break it down and turn it into natural gas. So same types of thing, you can collect all of the waste. This time it's not only food type waste and plant waste, it's now also sewage. So any cow sewage, any pig sewage, any sewage coming from chicken farms can all be collected together, digested down and produce natural gas. We actually have this in most sewage treatment plants around the United States. We'll have small versions of this. They do it out in Seattle, where they produce large amounts of natural gas that are actually used to make electricity. So this is being used around the world to actually produce electricity. They take the gas, they burn the gas, or they take that gas and they put it into a fuel cell, and that fuel cell then makes electricity. So the last one is actually doable right now. So methane digestion is a very efficient way of using leftover agricultural materials as well as sewage to produce energy. Again, the price is not competitive with using natural gas straight out of the ground at the moment. We need to get more efficient in our digesting works, the enzymes that we use to break down our nutrients so that they become methane. It's very close. It's only sitting at about 6 cents a kilowatt hour. But methane digestion is very close to generating electricity at the price that we need to be efficient. And if we're doing our agricultural wastes, then why not do all the rest of our waste? One thing that we could do is do a trash to energy system where we have an incinerator and you would burn your normal waste. And when we look at trash, municipal solid waste, we'll talk more about how to convert trash into electricity. And the last idea in this lecture on energy is not an actual energy source. It is energy conservation. By far the cheapest way to make more energy available is to just be more efficient with the way that we use energy. We are extremely inefficient at the moment in the United States and most more developed countries. We said way back at the beginning of the course that the second law of thermodynamics says every time you do energy change, useful energy is lost. Well, when we take the internal combustion engine, only about $1 for every $10 of gas you put in pushes the car forward. The car's that inefficient. It's the same with incandescent lights. Only about 10% of the electricity that goes into a normal light bulb makes light. So we are extremely inefficient at utilizing the energy that we provide. If we can be more efficient, you have more efficient engines, get more miles per gallon, then the gasoline will last as longer. Oil as a resource will last as longer. If we can use less energy in lighting our homes, like compact fluorescents, then there's more electricity to go around. So we have to burn less coal. So we need less solar power or wind power to generate the amount of energy we need. Instead of having engines, let's be more efficient and use fuel cells. Your textbook's got a whole chunk on how fuel cells are much more efficient because they've got no moving parts than normal engines and generate high quality energy very, very simply. So if we could just become more efficient, even though that doesn't produce more energy for us, it means that there's more energy to go around. Remember that the population of the planet is increasing. So every year there are more people trying to use energy. So if we continue as we are today, that just increases the rate at which we're using up our non-renewable sources. If we become more efficient, then those same non-renewable resources will last for much longer and will supply the needs of many more people. So we can switch. This is that south face house again, the energy efficiency house. And this is not, in fact, a light. This is a solar tube. It collects sunlight from the roof and with a series of lenses and mirrors focuses that light and passes it out into a room. It looks like there's a light bulb in there. It looks like the light is on to light that room. You can see the two lights each side of it, they're switched off. So this is just passing sunlight down into the room so that no energy is actually required to light this room during the day. There's no windows in the room, so normally it would have had a light in there and everybody coming in and out would have kept the light on. And what we're doing is we're lighting it more efficiently. We're just being efficient in our design. We've got more efficient water heaters, actually covering your water heater with a water heater blanket, insulating the pipes from the water heater to make it more efficient so that you use less electricity for the same amount of hot water. We've got an efficient front-loading washing machine, trying to be more efficient with using less water so that we don't have to heat as much water to do our daily washing. We've got a high efficiency dryer, drying the clothes using less electricity. Even better still, don't put them in a dryer, use a line outside. We've got more efficient vehicles. This one happens to be a plug-in station for an electric vehicle, so that you don't use any gasoline at all moving around. But that would only be good if we were generating the electricity in an efficient way. If we were using an inefficient power plant, then this really wouldn't help much. But as long as the electricity was actually being produced in an efficient, non-polluting way, this could help. And this is probably the number one thing that you can do to help. And that is when you buy products, actually look at their life cycle cost. You'll have done a worksheet on life cycle costs, so you should know what that is by now. And that worksheet and this slide is really just to remind you, when you buy things, if you buy the most efficient one, that is often, over the life of that item, the cheapest decision to make. And if you buy the things that are the most efficient, that tells manufacturers that they need to build more efficient things, and therefore we become a more efficient economy.